All right, so I assume it's midterm week because we have like 1, 2, 3, 4, 5, 6, 7 people. Joy. So that's good for you because this is going to help with the next lab you only have a week for. And you can probably finish it, not within this time, but you can probably get pretty close. So lucky for you. So yeah, or the midterm grades are back, so maybe that's another reason. Everyone was like, yeah, screw that. Or, well, the average was like 80, so that's pretty high. So maybe you thought that, yeah, the next lab's only worth 4%, so yeah, screw it, just don't do it, I guess. Whatever. All right, well, anyways, we will go into locking today, and this will help for lab 4, which apparently you will see again. That will be quite similar in another course, so it'll make that course a lot easier too. So we are just generally getting into locking, other difficulties, and we want to prevent data races. So as a quick aside, so of the like 7 people who are here, who's used Java before? We got some Java users. Have you ever used the keyword synchronized? Any synchronized users? One? So synchronized caused your program to crash, so you stopped using it? Yeah, neither did I when I first started with it. It was like, yeah, if some problem happens, throw synchronized on it, and it might work. All right, so these whole lock things, kind of a pain. So with object-oriented programming, especially with Java, developers want something easier to use. So basically, they were like, hey, you can say a monitor or a method is something called monitor, and let the compiler handle the locking for you, so I don't have to do a lock, colon, and unlock. And I'll make it such that only one active thread can be active in a monitored method at a time. So it's essentially a mutex over the whole method, so that only one thread can actually execute that method in an object at one time. So basically, within the object, the compiler will create a mutex for you, and every method you mark as synchronized, or whatever the keyword is in Java, it's synchronized, it will lock that method whenever you begin, and before it returns, it will automatically unlock for you. So it would look something like this. So if in Java I'm making like a bank account, well, I would have an int for the balance probably, and if I have a deposit and a withdrawal, well, it would increment or decrement that balance. And if I'm using a bunch of threads now, I know that I would probably have a data race involving that. If multiple threads are trying to change the balance on the same account, then we have the data race, the same count problem happens where we could get an invalid balance and all that stuff, and we'll see a thread example where we actually try and do this in C. But if you do this in Java, the compiler would essentially transform this into, it would lock a monitor whenever it begins deposit, do the balance, do the increment for you, and then unlock before the method returns. And then with withdrawal, it would use the same lock, so it would acquire it at the beginning and then end it at the end. And that way, if these are all the methods that use balance, you don't have data races anymore, we're all good. And the problem you probably had was that you forgot to mark when the method's synchronized, so you still have data races. So as soon as you forget one, you still have data races because one method isn't using that lock. So it's good to know what these things do under the hood, so you know you use them properly. So this was like a good idea that, you just make it easier, but if you just forget one keyword now, rather than a lock and unlock, your whole program doesn't work, so take and leave it. So we saw centerfors before with that consumer producer. It kind of got messy, and it was kind of hard to, like, what we were protecting against was pretty straightforward. We wanted to make sure we didn't empty something that was already empty or filled something that was already filled. But if you have more complex conditions that you want to ensure are true, it might be a bit more trickier to use centerfors. And there's another tool you can use in your synchronization toolkit, and they're called condition variables. And they're equivalent to centerfors, but they behave a little bit differently, and they make that block queue a bit more explicit. So They all must be paired with a lock, so you can create a condition variable. You can think of this this condition variable. It's not strictly true, but it's easier to think about that way. You can think of that condition as just being a queue. So you're creating a queue, you can create attributes, but we'll take default ones, and then you can destroy the queue. And then there's essentially two fundamental things you can do here. You can either signal on that queue, which will wake up exactly one thread that is blocked on that queue, and then the other one is you can wait. So you have to have a mutex paired with that queue, and what this function will do will essentially just put you in the queue atomically and then put you to sleep, and then the idea is you go to sleep and then another function can wake you up whenever the condition's true, and then you can continue going. So, and then there's also broadcast, which wakes up everything in the queue, but for the purposes of this course, we just have to talk about signal and wait. So they all must be paired with the mutex, so any calls to wait must already hold the mutex, like it must already be locked, while if you do signal or broadcast, you don't actually have to have the lock, it's not required. So why is that? Well, you can think of wait, it needs to add itself to the queue safely, so it can't have any data races. So it would necessarily need to be under mutual exclusion, and the idea is you're waiting on value anyways that you don't want any data races on, so you already need to have a locked acquired anyways. And then it needs that mutex argument before going to sleep, because atomically it will add itself to the queue and also unlock the mutex so another thread can go ahead, execute, hopefully make the condition true, and then wake you back up. So, and then whenever you get waken back up, whenever you start continuing that wait call, before wait actually returns back to you, it will try and reacquire that lock. So the lock is held when you call it, and then you go to sleep for an amount of time, someone signals and wakes you up, and then you have the lock again when you return, and you can keep on going. And then one mutex, if you want, can protect multiple condition variables, and again, we only need to consider wait and signal. So again, here's what wait does for condition variables, so which is different than the wait for processes, because we are not very creative bunches and we only have a few names that we use. So if you use a condition variable wait, when you call wait, again, atomically, this will all happen atomically, so either it all happens or it all doesn't. So it will add itself to the queue for the condition variable, it will unlock the mutex so another thread can go ahead and execute, and it will get blocked. So it will be put itself on that queue, can't execute anymore, and it's no longer scheduled to run. And that fixes our problem where we might not have gone to sleep yet. This all takes care of that we saw last lecture. So, yep. So if you have a lock and unlock, only one thread at a time will execute anything between those. Yeah, because after the unlock, any number of threads can execute you want. Okay, yeah, and for this, the wait too also needs another thread. Since it's on the queue, it's blocked, it's not executing anymore. It might be stuck there forever unless another thread called signal or broadcast wakes it up and it tries to acquire the lock again. So as soon as some other thread calls signal or broadcast, it will be unblocked, meaning that the scheduler can pick it to run. And if it gets picked to run, it will acquire the mutex again and then return from wait when it gets it. So then you're sure that you have the lock when you're done. So this is how we could change our producer consumer code. Instead of using mutexes, we could use two condition variables, and this might arguably be a bit clearer. So in here, instead of just having a mutex for counting the number of filled slots, we will just create a queue that says, hey, we will put things in the queue if all the slots are filled. And then we have another queue for everything waiting for an empty slot. So I'll call them has a filled slot, has an empty slot. So what we can do is, in the producer, we already had a lock before because we didn't want any data races. We create a mutex to go along with these condition variables. So we would acquire it, make sure we're the only ones with the mutex now, and then we can check our condition. So in this case, we're going to use n filled, where we just keep track of the number of filled slots instead of keeping track of the number of empty and filled slots. We'll just keep track of the number of filled slots. So if all the slots are filled, so if the number of filled slots is currently equal to the number of slots, well, we would wait. So we put this thread to sleep and say it's going to wait for an empty slot, and we give it the mutex. So if all the slots are filled, adds itself to the queue, and then puts itself to sleep. And then otherwise, if it goes ahead and makes it through this while, so all the slots aren't filled, it means it could fill a slot. It would increase the number of filled slots, which is okay. No data races because we're still between this mutex lock and mutex unlock. So we would increase the number of filled slots, and then we would signal has filled. So if there's any threads waiting for a filled slot, we would wake up one and say, hey, we filled a slot, you can wake up now. And then in the consumer, same deal, we would lock the mutex. Now our condition is different, so we check if we have no filled slots. So if we have no filled slots, we will put ourselves to sleep, put ourselves on the queue waiting for a filled slot. And then otherwise, if we make it through this while loop, we would just empty a slot. So we would decrease it by 1, and then we would wake up anything waiting for an empty slot, which would wake up a producer that would be waiting that would return from here. And then we unlock our mutex. So I could actually switch these two around if I wanted to. So any questions about this code as opposed to our solution for it using center fours that we saw, Thursday in the cursed room? Yeah.
What part of this sets the signal?
Sets the signal?
Yeah, when we're checking the conditions, what part of this changes the condition value?
So in this case, you have to manage the condition because our condition is this n filled slot. So we change it. So you just have to make sure that when you change it, you signal whenever you change it such that the other things could wake up and their condition is now true and they can pass. So yeah, so if I don't have the signal and I forgot to put it in, well, I can potentially, I increase the number of filled slots, and if something went to sleep because there were 0 filled slots, well, if I don't wake it up, it will never be woken up and we'll never check that the number of slots changed. Yeah, so we're offloading our post-wait problem by just making sure we call signal and wait. And thankfully, the wait goes in the same place. So any questions about that? So is this clearer than the center four solution or not? Ish, some heads yes, some no. Other questions, why do we pass mutex to it? So we pass mutex to it. So we're going to pass mutex to it because, again, atomically, we have to make sure that we add ourselves to the queue and that we don't have any data races in it. So because we're doing condition variables, we don't want a data race with a condition variable, so likely you're holding it anyways. So it can just take advantage that you actually have a mutex already, and it makes sure when you come back, it reacquires the mutex, so you also don't have any problems when you return from wait and wake back up. So before we call wait, we have the mutex acquired, so it's locked, and when we return from wait, it's also locked. So we don't have any problems where we return from wait and now it's unlocked and we have to acquire it again or something really weird. And we'll see an example. So let's go into fun problems we can have. So here's our problem. Yeah.
So pthread condition wait, that unlocks the mutex, right?
Yeah, before the thread goes to sleep.
Okay, yeah, that makes sense. So like inside of the function that is pthread condition wait, what it does is it unlocks the mutex and then puts the thread to sleep.
Yep, and adds itself to the queue. Yep. So 3 things that all happen atomically that you don't have to worry about races for.
So basically we set up a queue with this, the new stuff we introduced today, the init and destroy and all that.
Yep.
Condition stuff.
Yep.
And this is just a way to operate on that queue safely.
Yeah, the easiest way to think about condition variables is wherever you have this pthread con, you can think of it as just a queue. And like with mutexes, you have to init them, you have to destroy them, and then the only things that we care about for now is signal, which will wake up exactly one thread that is on the queue. If there's no threads on the queue, it does nothing, so it's fine. And then wait, which will put itself to sleep and do those 3 things all atomically. And then when it returns, it reacquires the lock. So we'll see that this is nice. This makes our life a bit easier, but we still have some issues. So let's take a minute, read this code. So there's going to be 2 threads here. One thread is executing pthread mutex lock, so they're both using the same mutex. So one tries to lock a mutex, check a condition, and then wait, and then the other one, and then unlock, and then the other thread just sets the condition to true, and then signals the other thread if it's in the queue. So let's give a minute to think about that, and I'll put it here. And just remember, because we're doing condition variables, the idea behind here is that at this line, after you wake up and you make it out of that while loop, well, the condition better be true at that line. Otherwise, you kind of wasted yourself, because now the condition you were waiting for doesn't hold whenever you were actually just waiting for it to hold. So the condition better be true at that line. Yep.
So deploy wait, like because it didn't put mutex on the thread 2,
Mm-hmm.
my signal deploy wait, which will be with where no signal.
Yeah, so short version of that was I don't have a mutex along or around my condition true whenever I set that. So I actually kind of have a brace with my queue. What could happen is thread 2 signals while nothing's on the queue, while the other thread could have checked the condition and saw it was false, and then it put itself to sleep after the other thread signaled. So yeah, that's our big problem we had, but we can see that if everything just went to completion, we're actually okay. So initially, let's assume we have our condition. So assume initially our condition's equal to false, and then we have 2 threads executing, and generally when you program, you assume that one thread happens and then another thread happens. So what will happen if I say thread 1 executes to completion first? So what's thread 1 going to do? Well, thread 1 is going to call mutex lock, and is the mutex currently locked? Hopefully not, nothing else. The mutex is just created, so it's unlocked. No thread has locked the mutex already. So it would now run that, acquire the mutex, and now thread 1 has the mutex. So if thread 1 has the mutex, well, it can continue going. It would check the condition. So that would be a memory read. So it would go ahead, read that the condition is false, and then go into the while loop. So it would go here, and then it's going to add itself to the queue. So cond here. we can think of it as just having thread 1 in the queue, and that's what's waiting. And now thread 1 puts itself to sleep. It can't run anymore. And then as part of putting itself to sleep, that mutex is now unlocked. It's all in the queue. So our mutex is also unlocked. No thread has the mutex, so it's all free. So then we execute thread 2. Thread 2 would check the change the condition from true or from false to true. So now our condition, which would be in a global somewhere, is now true. And then we would go ahead, signal, which would wake up thread 1 on the condition queue. So now thread 1 can wake up, and there's nothing on the condition queue. Thread 1 wakes up, and if it gets scheduled, it would now try to acquire the mutex, and when it returns from wait, it would have the mutex. So after we return, thread 1 has the mutex, and we would have returned from pthread wait. Now we would go back up to the top of the while, check the condition again. Now the condition is true, and I just deleted everything. So now the condition's true, and it would just drop here. So now we're executing that line where the condition better be true, and it is true, so all good. And then it would unlock the mutex. So now no thread has the mutex. All right, any questions about that? That seemed to work how I intended. Okay, well, then let's rewind. So rewind, initially the condition is false, and both threads need to execute. So what's going to happen if thread 2 executes first? So thread 2 executes first. We should just change that condition from false to true. And then it would call signal. What would it wake up? Nothing, nothing's in the queue, so it does nothing, so which is fine. Then in thread 1, it would try and acquire the mutex. Nothing's currently holding it, so it could pass. And now thread 1, whoops. Thread 1 has the mutex. It would go ahead, check the condition, which would read true. And then it would go here, break out of the while loop, that line, condition's true. Perfect. All right. So now, knowing that something bad can happen, let's reset everything. Whoops. Who wants to tell me a very bad interleaving of when something goes very, very, very poorly? Yeah. Yeah, so so the suggestion was that, hey, I have a problem if thread 1 starts first and then I get yielded or switched away right at that line. So let's make it crystal clear what happens. So thread 1 executes, grabs the mutex because it is the only thread. Or sorry, it's the first thread there, so it acquires the mutex. And then it would go ahead, check this condition. And right now, that condition, that condition is false. Whoops, I should have deleted that line. So that condition's false. And now we get context switched over and start executing thread 2. So in thread 2, we change that condition from a false to a true. And then we signal anything waiting for the queue. So does it do anything? No, because there's nothing in the queue, so it does nothing. Then eventually we context switch back over to thread 1. Thread 1 keeps on executing. It would just add itself to the queue and then put itself to sleep and unlock the mutex. So we go here. The mutex is now unlocked. And thread 1 is in the queue. And now we are completely screwed because no one will ever signal it again. So thread 1 will be infinitely stuck and you won't know any better. So any questions about how that works? Because that is bad. How would I fix it? Yeah. Yeah, I could add a mutex to thread 2. Where do I need my mutex? Sorry? When I set it to true, okay. When I set it to true, where do I need a lock then? Yeah, so I just want to kind of do a lock and unlock around my condition variable. So lock that mutex. And then where should I unlock it? Right after or after the signal? Well, let's go ahead and do it after. So now with our new modified code, well, what's going to happen? So our bad thing happened after we read this false, right? So after we read this false, so right after we read this false, thread 1 had the mutex, and there was nothing in our queue because we just read the line and we were rewinding a bit. So we just read that false line and that's it. So our problem before was when we context switched over to thread 2, it it updated the condition value to be false. So sorry, it's currently false now. So now what happens if the scheduler decides to context switch back over to thread 2, it would try and lock the mutex, and that doesn't work because the mutex is currently being held by thread 1. So it can't do anything. So depending on the mutex implementation, it could just spin, try over and over and over again, or it could put itself to sleep, which is, again, another fun queue. But you don't have to worry about managing that queue because the threading library or the operating system will go ahead and do that for you. So in this case, as much as thread 2 tries, it's not going to execute anything. It's waiting for that lock call. And then whenever thread 1 goes again, it would add itself to the queue. Well, let's put that mark. It would still be executing this wait. So it would add itself to the queue all atomically, and then unlock the mutex, again, all atomically. And now if we switch back over to thread 2, well, no thread holds the lock anymore, so thread 2 could actually get the lock. And then update that condition to be true. And you can see here why it's important that everything's protected by the mutex. So even before here, like there could be a signal here, and that's fine, but you don't really want thread 1 to do anything until you actually update that value, and it wouldn't because thread 2 still has the mutex, so even if it woke up before it returns from wait, it would try and reacquire the mutex again, and right now it can't get it, so it can't return. So even if I have a signal there before I change it, it can't do anything. And it's essentially I would wake it up early and it would not be able to proceed anyway, so why even bother waking it up there? So in this case, thread 2 acquired the mutex, changed the condition from false to true. And then it signaled, so now it removed thread 1 from the queue. And now it's scheduled to run, or not scheduled to run, but it could be runnable. And now say the operating system decides to run thread 1 at this point. Well, as part of returning from wait, again, it would try and acquire the mutex. And right now, thread 2 still has it, so it would never return from wait until thread 2 actually reaches the unlock call. So this isn't bad that I have the signal here, but I'm waking it up when it can't do anything. So typically you want the signal after the unlock, but for correctness, it doesn't matter. I'm just maybe wasting some more time. So then I unlock, and then now no thread has, now no thread has the lock. And then thread 1, which is now able to run, would go ahead, acquire the lock before it returns from wait. So whenever it returns from wait, you are sure that you have the lock. So thread 1 has the lock. And now it would go ahead and check again, and that condition is true. So it goes out, and now the condition better be true on that line, and I'm all good. All right, so any questions about that? That works, right? Okay, well, I'm checking conditions that don't need to be checked. What about if I do that? So I'm starting to notice every time I wake up, the condition's already true. So why the hell am I rechecking it again? I'll just go ahead and put an if there. So if it's false, I'll put myself to sleep, and then when I wake up, I know it's true. Yeah. Nope. No, because, so the reason you don't want to do this is because in this case, it's actually fine, because no matter what, that condition is going to be true, because I only change it from a false to a true once, and it's no problem. But typically, you'll have code that looks like, not that, this. So thread 1 is exactly what we saw before, except we changed that while to an if, and then we want to know what could happen here. Ideally, we always want the condition to be true at that line. And then let's say, usually you don't just have a value go from false to true and that's it. Typically it changes all the time. So let's come up with thread 2 that changes it to true, like we said before. And then since we're changing it to true, we would want to signal, wake up any thread that's waiting for it to be true. Then another thread might set it to false. So if it sets it to false, that's fine. It doesn't have to do a signal because the condition's now no longer true. So with this, let's look at it for a bit and think of anything bad that could happen here if that while is now an if. Yeah.
So another, after the wait has been called, some other thread does something that modifies a condition, and we come back, and it's in a situation where we would want to go back and run the wait again. So we want to check the while of the not condition. I'm not doing a good job explaining that, but something has changed the condition outside of this thread, and it means that we don't really want to go on from waiting.
Something has changed. So thread 1 went to sleep because the condition is false. And then something else woke it up because the condition's true. Here, go there, yeah.
Thread 1 runs till wait, thread 2 runs, and then changes context after dropping the lock, and then thread 3 runs, which swaps it back to false. And then thread 2 picks back up and sends the signal, even though the condition isn't true anymore.
Yep, yeah, but it could, but okay, for yours, would it still happen if I move the signal up inside of here?
I don't think that still happens in this case.
Okay, and yeah, sorry, one more? Okay, yeah, you're good? Okay, so what could happen is kind of, kind of what you were saying, where thread 1 checks the condition, it's false, it puts itself to sleep, and then another thread sets it to true, wakes it up so it can potentially run, but before it's run, something else changes it to false. And now, if it wakes up, the condition would actually be false instead of true now. So let's see that real quick. So let's illustrate the badness. So initially, let's assume that our condition is false, and then cond what's in my queue is nothing, and who has the mutex? I'll just write the same thing. No one has the mutex. So badness that could happen is thread 1 executes, it acquires the lock, so it now has the lock. So right now, if any thread gets context to, it will never make it past that lock call because thread 1 has the lock. So right now, we don't have to worry about any data races on condition because no other thread can write to it, so we're all good. And also, speaking of data races, another way to think about data races is, like the less informal way to think about is, a data race is any time you actually now have a still value. So the data you read is now not consistent with whatever is the most up to date, and bad things could happen, as you may have discovered in lab 3, or you might still have to fix in lab 3. Remember that seg fault thing. Anyways, so in this thread 1, we check the condition, it's false, so we would wait and put ourselves in the queue. So atomically, we do all of this, we put ourselves in the queue, and we unlock the mutex. So now we are waiting for it, and in this case, again, instead of while, we put in an if here. So, yep.
So to summarize what's going on, we have some condition that we want to be true in order to run the stuff in thread 1
Yep.
after that if condition statement.
Yeah.
And so in order to ensure that, we're checking the condition, and if it's not the condition that we want yet, we wait, and then we put ourselves at the back of the queue or take ourselves off of the queue, and then the other stuff runs. And now in thread 2, it sends the signal to the wake up thread 1.
Yeah, so you can't take yourself off the queue. You can only add yourself to the queue.
Okay.
The one calling signal will take you off the queue and let you run again.
Oh, the queue is the waiting queue?
Yeah, you can think of this as like an explicit waiting queue. So if a thread calls wait, it puts itself on the waiting queue and goes to sleep.
Okay. So basically a signal is sent, so that's going to wake it up. And if it's going to wake it up, but in between then, thread 3 runs and changes the value of the condition.
Yep.
Okay, got it.
Yeah, so in this case, the condition's still false. We go to sleep because we're waiting for the condition. And then, so no one has the mutex. We're in that explicit waiting queue. And now thread 2 could execute. And it would pass this lock call because, well, no one has the mutex. So it could acquire the mutex. Then it would change the condition now to true, which is good. Yeah, changes the condition now to true. And then the condition's now true, so we can go ahead and signal, well, first we would unlock, so now the mutex is now not up. And then we wake it up. So we would wake it up, and now it is runnable, but it's going to try and acquire the mutex. So what we'd like to happen if things go well is right now at this point, the condition changed to true. So if it wakes up, the condition's true, that's good. It can continue executing. It wouldn't actually have to recheck the condition because it knows it's true. But what could happen is because before wait returns, it needs to acquire the mutex. Well, thread 3 could have already been waiting for it. So thread 3 is here. The mutex is unlocked, so it could acquire it. So now thread 3 has the mutex. Oops. So thread 3 has the mutex, changes the condition to false. Whoops. Changes the condition to false and then unlocks. So now our condition is false. No one has the mutex. And now thread 1 can wake up. It would acquire the mutex when it returns from wait. So it would have the mutex. And then because we don't have a while loop, we could read the most up-to-date condition if we wanted to, but we don't because we had an if statement here. So now we're executing this line and the condition is false, which is what we don't want. So any questions about that? And the same thing would actually happen if we move this up here. So it would have woken it up, but it can't grab the mutex. Yep.
So when we call signal, it wakes up the thread, but it's not necessarily immediately running, right?
Yeah. So you can think of it in terms of your threading library. Whenever you call signal, you just throw it on the ready queue again.
Okay.
So it could run, but not necessarily.
So we kind of have two queues. You have the actual ready queue of threads that can be run. Then you have this other condition kind of queue that you can be thrown on as like a waiting queue.
Yeah. Yeah. Potentially, it's queues all the way down. Potentially, we have 3 queues. So we potentially have a ready queue that the kernel is managing for all the threads. And then remember, we looked at the mutex implementation and said it had to be fair. So the mutex would have a queue in its own to make sure everything acquires the locks in order. So the mutex would have a queue, and then the condition variable's another queue. So here we potentially might have up to 3 queues. So, and this is why even with the mutex, so when it returned from wait, ideally we would have liked it to run after thread 2, but it just woke up and is now runnable. And if 3 tried to acquire the mutex first, it would pretty much be guaranteed to acquire the mutex before the thread that just woke up, and that's where all our problems arise. So it's not immediately runnable. All right, any questions about that? So that is fun condition variables, and believe it or not, they're supposed to make your life easier. So like with the first example where we could get away with changing that condition to be an if and it being okay, in general, if you don't want to think about it, just make sure it's a while and you recheck it over and over so you don't have to think about it, you don't run into this problem. There's only like very few scenarios where if is okay. Generally, make it a while if the condition goes back and forth, and make sure you read the most up-to-date thing. And that's, data races in a nutshell. So they serve a similar purpose to center-fors. So center-fors are actually like a special case of condition variables, so you could think about it the same way. So Your condition is an integer. If the value of the integer is 0, you put yourself on a waiting queue. Any thread that posts up would also signal, and they wake up, works the exact same. So generally, if the solution is suited exactly for a center for, just use a center for. It's simpler. If it's more complex, if your condition is not just a simple number, use a condition variable because it will probably be a lot clearer, right? They're equivalent to each other, so you could write one in terms of the other, but it's degrees of messiness and readability. So just use that ground rule. So for integer values, use a center for. For anything that's more complex, probably use a condition variable. And then next thing, lock granularity is the extent of your lots. So you need locks to prevent data races. But if you lock large sections of your program, it would probably be really, really, really slow because you're essentially making only one thread at a time, and now it's serial. What you could also do is divide the locks and use smaller sections so you lock as little as possible to prevent a data race. Like, what if you want to parallelize your hash table? Hey, lab 4. So other things to think about locks are like the overhead. So creating and destroying locks and the lock and unlock calls aren't free. So you probably don't want to overuse them. But again, you don't want to underuse them because you might have contention. So if a lot of threads are battling for the same lock, essentially that's all going to be serialized and your performance is going to be really, really bad because only one thread's doing it at a time. And then you also have to consider a fun thing called deadlocks if you have multiple locks. But with the locking overhead, again, you have to allocate some memory for the lock. It's going to take time to create them, destroy them, time to acquire them, time to release them. And the more locks you have, the worse this is going to get. So for your hash table thing, sure, it might be safe to just make, 20,000 locks or 1,000,000 locks or something like that, but that's going to waste a lot of space. It's going to waste a lot of time. But the big problem you'll have with multiple locks is deadlocking, which is something you don't want. So conditions for deadlocking is you have mutual exclusion, which is going to happen if we're just talking about deadlocking for mutexes. So mutexes guarantee mutual exclusion, so only one at a time. So of course, that's what happens for simple locks. The more important ones are hold and wait. So if I have a lock and I try and acquire another, I might deadlock. Another one is no preemption, so you can't take locks away. If I could take locks away and say, hey, no, you don't get to use that, then you could prevent a deadlock by just breaking the cycle. And then fourth one is, the cycle, the circular wait. So you have a lock and you're the one with the lock and you're waiting for another lock held by a different process. So that would look something like this. So consider we have two locks, two threads, and in the implementation of thread 1, I try and acquire lock 1, then lock 2, and then I release them both. And thread 2, I do it in the opposite order. So I try and lock 2, and then lock 1, and then I release them. Well, a bad thing that could happen is that thread 1 executes, it acquires lock 1, and then I get context switched over to thread 2. It acquires lock 2, and now I'm screwed. So if thread 2 starts executing, it tries to get lock 1, which is held by thread 1, so it can't do anything. And now in thread 1 that has lock 1, it tries to get lock 2, which is held by thread 2, so it can't do anything. So it's like, they're holding each other hostage at this point, and no thread can make any progress. And if no threads can make any progress, that's what we call a deadlock. So you have to prevent these. And we'll go over it in more detail in the next lecture. And so just remember, pulling for you. We're all in this together.